Next, periodic trends. Periodic trends can be seen in the 6 properties listed above: atomic radius, ionic radius, melting point, ionization energy, electron affinity, and electronegativity. When looking at the periodic table, trends of these properties can be seen across and down the period. First, it is important to know what they are. Atomic radius is the distance from the nucleus to the outermost electron. It increases down the group as the outermost electron is in a higher energy level, making it further away from the nucleus. This increases the shielding effect. Shielding effect refers to the core electrons in the inner energy levels of the atom, repelling or shielding the electrons in the outer valence shell, and therefore decreasing the force of attraction between the valence electrons and the nucleus. This reduces the positive nuclear charge experienced by the valence electrons. On the other hand, the atomic radius decreases across the period as electrons are being added to the same energy level, but the number of protons increases, which attracts the electrons closer to the nucleus. This increases the effective nuclear charge, which is the net charge experienced by an electron. Z refers to the nuclear charge, representing the atomic number, and S refers to the charge that is shielded by the core electrons. Technically, effective nuclear charge takes into account all the attraction and repulsion going on inside the atom. The ionic radius can be distinguished by cations, which are positive ions, and anions, which are negative ions. Cations contain fewer electrons than protons, so the electrostatic attraction between the nucleus and the valence electron is greater, making the ion smaller than the parent atom. Anions contain more electrons than protons, making the ion bigger than the parent atom. Also, the periodic trend of the ionic radius follows that of the atomic radius. Next, melting point. Melting point depends on 2 factors: the structure of the element and the type of attractive forces holding the atom. Now let's look at the periodic trend. Elements across period 3 show different characteristics in their melting point. Metals such as sodium, magnesium, and aluminum show an increase in melting point across the period as the number of valence electrons increase. Silicon has a macromolecular covalent structure with strong bonds, resulting in a very high melting point. Nonmetals show simple molecular structures with weak intermolecular forces, resulting in a low melting point. Halogens, such as argon, exist as a single atom, resulting in an extremely low melting point. For group 1, melting point decreases down the group as the atom becomes larger and the strength of the metallic bond decreases. For group 17, melting point increases down the group as molecular forces between the diatomic molecule increase down the group. Next, ionization energy. As you can see, the term ionization energy is highlighted in yellow. The vocabularies highlighted in yellow are frequently tested by IB. IB might ask for the definitions of these terms. Keep this in mind. Ionization energy is the minimum energy required to remove an electron from a neutral gaseous atom. The equation shows a neutral gaseous element X, receiving energy and splitting into a positive ion and electron. The energy required to conduct this equation is known to be the ionization energy. The ionization energy decreases down the group as the outermost electron is further away from the nucleus, and so less energy is required to remove it. On the other hand, the ionization energy tends to increase across the period as electrons are being added to the same energy level, and the extra protons in the nucleus attracts the energy level closer, making it harder to remove the electron. I will emphasize the phrase tends to, because the values do not increase regularly across the period, because new sublevels are being filled. Let's look at some examples. As you can see on the graph at the left-hand side, the elements across period 3 show an overall upward trend. However, there are some drops in between. For example, the ionization energy of sodium and magnesium increases and then slightly drops at aluminum. This can be explained in detail by looking at the electron configuration. The order of magnitude of ionization energies of these three elements are as shown above. Aluminum is higher in magnitude than sodium because the p sublevel is in a higher energy state than the s sublevel. However, magnesium is higher in magnitude than aluminum because outer electrons in magnesium are fully filled, which makes it more stable. Outer electrons in aluminum are incompletely filled and so unstable, which makes it easier to remove. Next, electron affinity. Electron affinity is the energy change when an electron is added to an isolated atom in a gaseous state. The equation shows an electron adding on to a neutral gaseous element X and becoming a negative ion. Trends in electron affinity is not well highlighted compared to the trends previously learned. However, the electron affinity becomes less negative down the group and becomes more negative across the period. Becoming more negative means that the reaction is more of an exothermic reaction and so releases more energy in the process. Electronegativity is a relative attraction that an atom has for a shared pair of electrons. It decreases down the group due to the increase in atomic radius and shielding effect. And it increases across the period due to the decrease in atomic radius but increase in effective nuclear charge. The term electronegativity is frequently tested in IB and comes up frequently during this course, so it will be really nice to fully understand this concept. This is an overall illustration of the periodic trends going down and across the periodic table. You can always refer to this drawing for a clear overview. Now let's look at basic trends in Group 1. Group 1 is known as the alkali metals, and the elements all have one electron in its outer shell. They are good reducing agents, meaning that they readily react by losing their outer electron to form metal ions. The reactivity increases down the group, as the outer electron is in successively higher energy levels, so less energy is required to remove it. They also react with water to form alkali solution of the metal hydroxide and hydrogen gas. In the case of lithium metal, the metal reacts with water to form lithium hydroxide and hydrogen gas. This reaction is slow and shows slight bubbles. However, as the reactivity increases down the group, the reaction of the alkali metal with water becomes more explosive. In addition, the metals react with chlorine, bromine, and iodine to form ionic salts. For example, sodium reacts with chlorine to form sodium chloride, and so on. How about Group 17? Elements in Group 17 are known as halogens, and they have 7 electrons in the outer shell. This makes them a good oxidizing agent, meaning that they readily react by gaining an electron to form halide ions. Their reactivity decreases down the group as the outer electron is in successively higher energy levels, so further away from the nucleus, which decreases the attraction for an extra electron. Also, halogens can react with halides, and the more reactive halogen will react with a less reactive halide. As I mentioned before, the reactivity decreases down the group for halogens. So, fluorine will have the highest reactivity. Looking at the chart, we know that chlorine has the highest reactivity, so it will react with the less reactive halide ion. Also, a test can be conducted to find the presence of halide ions, in a solution by adding silver nitrate. The silver ions will react with the halide ion to form a precipitant of the silver halide. Looking at the color, we can detect the kind of halide that was in the solution. Let's look at trends in period 3. Metals can be distinguished from nonmetals by their chemical properties. For example, metal oxides tend to be basic, and nonmetal oxides tend to be acidic. These metal and nonmetal oxides react with water to produce acid and bases. Some interesting points to notice about these reactions. First, we can see that metal oxides form bases when reacting with water. Second, aluminum oxides are classified as amphoteric oxides, meaning that it can act as an acid or base. Third, silicon is a metalloid. However, its oxide is acidic, and it does not react with water, but it reacts with sodium hydroxide to form sodium silicate. Lastly, nonmetal oxide, such as phosphorus pentoxide and sulfur trioxide, reacts with water to form acids. However, despite the fact that chlorine has several oxides, it cannot react directly with oxygen, which is similar to that of argon. It is important to know how to write the reaction equations and understand their difference in pH. This is it for topic 3. See you in the next one.